Okay, welcome to today's lecture. So last time they had some tech issues and the recording doesn't have audio. So today we're probably going to spend like 1 or 2 minutes to check if the audio is actually on for the online session. Oh, looks like it's on. Can anybody check the online recording stream for me and see if it has record? I can check. Okay, I feel like we have here. All right, I'm just going to put it right here. Okay, great. Hopefully this time it will get through so that people on the online stream can actually listen to the recording. Welcome to week 3, and we got a couple of announcements. So actually we're going to release assignment in week 3, not week 2, because you need to learn about the SQL query language to actually do the assignment, and we will add more test cases to the assignment. So we'll probably do that by the end of the week. And for quiz 1, we got almost everyone submitted to week quiz 1. So probably like 40 people didn't submit to quiz 1. And most of people got full score, which is expected because quiz is supposed to be pretty easy. And don't forget that quiz 2 is due on Friday at midnight. So here's the thing about quizzes. So they're here to kind of push you to learn the week's content. So and they don't really constitute a large proportion in terms of marks. So and also because last week it was the first quiz, right? Maybe you didn't know there's a quiz. So if you didn't attempt the quiz, we'll figure something out. And if you, for instance, if the quiz is due on Friday and then we haven't released answer it because we're releasing the answers on Monday, and then you got sick on Friday, you didn't apply for special consideration, because most of the times if you apply for special consideration that at that short notice, they will not approve it. So if that happens to you, just send us an email and let us know what's going on, and maybe we can work something out. So because this is not a huge, I don't want a quiz to be a problem for you guys. I don't want people to lose marks because they forgot to do the quiz. So it is meant to push you to study, and it's not meant to take your marks down. So if that does happen to you, please, for instance, on Friday night you have a fever or something and then you didn't do that, or you forgot about that, before we release the answers, let us know, and we'll review your case. We'll review it case by case. And up until now, 560 people have set up PostgreSQL in VXDB server. Is some progress, but we would like to see like everyone to have logged into the server, because that's the only way you can practice with PostgreSQL. And we'll also be having help. We have arranged help sessions on week 4 and week 5. Those weeks are very important for you guys because you'll be heavily involved in the assignment. Right. I'm just going to really briefly talk more about what to expect from the assignment, and then we'll move on into SQL queries and how to actually write SQL queries. So we have already talked about data definition language. I've talked about data manipulation language. We learned how to create tables, and we learned how to add constraints to tables. And we have learned how to specify primary key constraints, how to specify foreign key constraints. And today we're going to take advantage of those constraints, especially the primary keys and foreign keys in those tables to help us do the actual query. So this is this, the database schema that we have talked about last Thursday. And I don't think we need to talk about this, the database itself more. Just a few tips for the assignment when you actually get to do it. The recommended way of doing it is that you make a directory within your dedicated folder, which is named after your ZID. So it's in local storage, your ZID folder. And then make a folder called assignment 1 or something. Most people call it ASS1. And in that folder, you want to copy all of the files. We'll probably give you one dump file. You want to copy the file into your folder and then create a database. And then we'll also be giving you a ASS1. I'm not going to pronounce it because it sounds bad. It happens in every, I think it happens in every course that they ended up pronouncing it and it sounds very bad. So ASS1 SQL file is the only file you'll be submitting. We'll be creating a lot of like skeleton code, the template for you, and you'll need to fill things in that template to complete the SQL statement and complete the view statements. And each part of that file should answer one question in the assignment. And in the end, we'll test that in our server. So basically, you need to create a database, load the data, load the ASS1 dump. It will create a database for you. And then you need to repeatedly revise the SQL file you need to submit. So SQL file will basically define a bunch of select statements as well as create view statements at this point. And yeah, you'll be adding SQL code to that file only, and this is the only thing you'll need to submit. You don't need to submit to us the whole database. The only thing that we need is those SQL definitions. And it will generate a bunch of messages like create view. And if it does generate error messages, please look into it, because if you fail to handle any error messages, we'll take some points off, because it shows that you don't understand how create view statements or SQL statements works. So definitely make sure that it passes the syntax check before you do anything, before you submit to us. And you repeat the process until the views and the functions are created. And we'll be giving a script to test whether your queries and functions actually give the expected output. And we'll also be specifying the expected output too. And so repeat that until everything works fine, everything works well. Okay, that's enough with the assignment tips. So let's jump into the SQL querying language. So we have already talked about data definition language. We've talked about data manipulation language. Now this is actually the part where people use SQL the most, data querying language. So this is a classic select from where block. So the way we tackle questions in SQL is that we want to really understand the schema, well, and we want to really understand the questions well. And the first steps are almost always, well, always, I'm going to just say put always. The first step is always to identify the relevant tables, the relevant relations. So we use table and relations interchangeably in this course. The first step would be to identify the relevant tables in the database that we'll be using in our query. So select from where block is basically selecting the columns from the tables, and then we put the filtering conditions in the where clause. And I think we should start with simple queries, and then after that we'll talk about how we can actually join tables using foreign keys, and then how we can order tables order the results based on a specific. Damn, I think she forgot her phone. just gonna put it away. And after that, we'll talk about how to group by some columns if that's needed. So this is a classic select from where block. So after from, you always put the table names. And in select, after select, you want to put the column names that are specific to the tables. So for instance here, we're talking about a table called R. So this could be a student table. And A, B, C, D could be student ID, student age, program, stuff like that. And B and C are actually the columns from that table. So one thing that one scenario that we could encounter is we might ended up selecting from multiple tables where they have different attributes, but the attributes take after the same names. For instance, what happens a lot is we have a student table, we have an enrollment table, we have a course table, and they all have some attribute with the same name, which is ID. So we could have ID in the student table, we could have ID in the course table, and we could have ID in the enrollment table. And how do we know which ID we're talking about? So SQL handles this in a very easy way. So basically, we can treat it as if it's an object-oriented language. We can just do table name dot column name. So we can distinguish them by saying this is the student.id, this is the enrollment.id, so that to make it more specific. So imagine if you're selecting from different tables, and imagine you're selecting from two tables, and those tables, both of them have the column B, and when you're selecting B, from those tables, the SQL got confused, so you need to specify what B column you're talking about. You'll say R1.B and R2.B after select so that it knows which column you're talking about. And join is the most important part in SQL query, because without joins, we can only do single table queries, which are easy and fun, but we're not going to go very far with just single table queries. For single table queries, we can just get away without using the joins, just by we can just learn select from where, and then we can just play with one table and be with it. But if you want to merge information from multiple tables, which is exactly why we model the database like this in the first place. The reason why we model database like this in the first place is so that we store different information in different tables, and when we want to ask complicated questions, we can find the corresponding tables and then join them and find the result. So let's say if you want to just find, so this is the assignment 1 table. If you want to find what matches took place in Sydney, then you only need to query the match table. And if you want to ask questions like, tell me the teams that had a match in Sydney with, and it is their home court, then in that case, you need to consider both information from match, and you need to consider the relationship which is involved, and you need to consider the table teams, and obviously you need to join those tables together to grab that information. And the reason why we had foreign keys is to make the join more well-defined, and we can actually effortlessly write join queries by just looking at how foreign keys are defined in the table. And we'll give more demonstration of that in the second lecture today. Okay, and also with SQL, we can have some type of aggregation. We can summarize the values in a single column. So basically, given a column of marks, we can extract the maximum mark, the minimum mark, the average mark, or even the median mark. And what's beautiful about SQL is that these are built-in aggregation functions that you can just use. And also, if you want to do something that is more complicated, for instance, in the stock market, they might be interested in moving average of 10 days. They might be interested in something more complicated aggregation where you want to look at a bunch of strings and then you want to aggregate them. And if you want more functionalities, you can also define your own aggregation. And we'll probably talk about that on Thursday's lecture. And also, it supports set operations. So we can take two sets of objects, and we're allowed to make the union of them. We can allow to make the intersection of them. We can make the difference of them. So union, the concepts of union, intersection, and difference, you should be familiar with it if you have taken discrete math. Yes?
Like if one table using the foreign keys to references to the other table, one should use the arm to show the rule. Why cannot it automatically know which one is the foreign key?
Can you make your questions clear?
For the enrollment table,
Yes.
we use the student ID, but student ID is references to the student table.
Yeah, exactly.
We use the arm to show that maybe enrollment.id equals to student ID.
So you're talking about how we write the joining conditions in when we're joining different tables based on foreign keys. So we'll get to that when we actually see an example. So basically, the reason why I said foreign keys are very useful for helping us writing joining conditions is because, for instance, in enrollment, you have student, you have course, and you have mark. And student is referencing student ID, and then course is referencing course ID. And then if you want to join those three tables together, you can just select a bunch of columns from these tables. And then in the where statement, after the where clause, you can specify that, okay, student ID equals enrollment.student. So this will link these two tables together. And then you'll also specify that course ID equals enrollment.course. So basically, based on the definitions of these tables, because we have seen how we can create these tables using create tables commands, and then we'll specify the foreign keys. And when we are joining them together, we're basically reiterating the foreign keys. We're saying that these should be connected and these should be connected. We'll just be rewriting the foreign keys and to join those tables. So that's why it should be easy from the foreign keys.
Why can't it do it automatically?
Pardon?
Why can't it do it automatically, like by itself?
What do you mean automatically?
If it knows the foreign key is referencing the other one, why do we have to say on this and that? Why can't it just compare it?
Well, at the end of the day, you still have to write the query for yourself. So if you want to join so I think what you're getting at is that if you want to join two tables together and we know the foreign keys, why do we need to write the where condition? Well, because if you're only talking about two tables, then it is clear what condition we write there, because there's only two tables, there's only one foreign key. If we want to join like a bunch of tables and all of them has like a primary key called ID, then sometimes it's not very clear exactly what to put there, because you ended up with so many conditions, and it's not obvious which ID you're talking about. So that's the reason. So you need to specify whether your column is joining this table's column or your column is joining another table's column. So you need to specify how you want to join the tables, because sometimes there are more than one way to join the tables as well. So here we're kind of oversimplifying things by saying that it can give us an idea. So I'm going to rephrase that. So foreign keys can help us write the join conditions. I'm not going to go so far to say that foreign keys can be translated into the joining conditions. So when we get to more examples, and you will know what I'm talking about. And we can also do grouping and group filtering. So let's just say that everyone has a different program in this class, and we want to group by the school you're with. So maybe we group engineering students in here. We group architecture students in here. I'm not sure if they're actually taking this class. And we're grouping math students in there. And maybe we want to know something about different groups. And in that scenario, we'll need to group. We need to use the group by syntax to get that information. And one common mistake beginners make is that they're confusing the having syntax with the where syntax, because having syntax can only happen when we are grouping things. So let's just say that we're grouping by degree, and then SQL will just get all of the group you guys into different degrees, and within different degree, it will look at your marks, and maybe you will get the highest marks in different degrees, or maybe you will get the number of students in different degrees. And having is just an additional filtering condition within that group. So let's just say that for each, we want to group by degrees. So we want to get math students here, engineering students here, and we want to get architecture students here. And now I want to have an additional filtering condition after grouping. Then I can say that, okay, within each group, give me the brightest students. Maybe give me, students with marks higher than 90 or something. Then this is where we'll be using having, because having only occurs after we divide people into groups. And if you don't group people, then more often than not, you're looking for the where clause. So it will directly apply the filtering onto all of the tables that you have specified. And also in where clause, you can also specify where is that column coming from. So here, employee has 3 columns, and you're saying that you want to maybe the B column, maybe this is salary. You want filtered employees with salary 50,000. And if we have another table here with the column B, then B itself will be confusing. So we don't know where we apply that filtering condition. So here we need to specify that this is the column in the B table, in the E table. So here we're creating an alias for employee, and we're saying that this column is from the employees table. So if you don't create an alias for it, we'll just write employee.b. So sometimes people get lazy and then they create an alias like this, and then they specify where that column is coming from. Okay, so these are the common functionalities in SQL queries, and now let's get to the implementation. So the reason why I said quote-unquote implementation of this syntax is because this gives you an idea of the most naive implementation so that you understand what it does. But under the hood, it will do vastly more complex things than this to make it faster. So for instance, what does this query do? Select some columns or all columns from a relation, from a table that satisfy the where condition. So the most naive way of understanding this, you can imagine there is a for loop going on that visit every row in the table. So we got a giant table, and then we wrote a for loop for I in 0 to 99. So that would be 100 rows. For each tuple, we check whether that tuple satisfied the conditions specified in the where clause. And if the tuple satisfies this condition, we include it. So that's the I would say pseudocode of the select from where block. But the reason why I say this is pseudocode instead of real code is because depending on what you're querying and depending on the filtering conditions, SQL is actually very smart. It will not it will not always do that, because if you look at this, what is the time complexity of doing this? If you're like in big O notation, what is the time complexity to do a simple select from where query? If we follow exactly this algorithm, what is the time complexity? Pardon?
The number of elements in R.
Yeah. So the number of elements in R. So if we call that, so basically linear, it will scan the whole table. And we know that a lot of times, if you actually play with the database, you know that that's not true, because the table can get very, very long, had 1 million rows, can get 10 million rows. And if you always scan the whole table, then it's not a very good practice. So what ends up happening is that they'll use pre-filtering, they'll use indexes to reduce the search scope, and maybe they'll sort the tuples in a way, and they will only look at certain tuples. So to make that time complexity much better. And so here, as beginner, you can just treat it like it is always doing the linear scan, so that you can understand what it is doing better. But you don't have to worry about the efficiency part of this at this stage. So basically, we scan every tuple in the table, and then for every tuple, we check whether the condition is met. If the condition is met, we include it in the result set, and in the end, we print the result set to you. So that's select from where, and join is slightly more complicated, and so this is a nested for loop. So if we're joining two tables, then what effectively if we're joining two tables based on the condition, what we're doing here is that you can imagine doing a nested for loop. So you're iterating every tuple from the first table, and then in that iteration, you also visit every tuple in the second table. So and then when the join condition is met, we check the condition in the where clause. So basically, this could be we're joining the enrollment student. Then for every student, we look at the whole enrollment table, and then we check whether my student ID matches the enrollment record. And then we check, let's say the condition is the student is over 30 years old. And after we have checked the student IDs in student and courses in enrollment are matching, we go ahead and check the student's age. And what is the time complexity of that? So that should be like even more, right? So that just say that the number of tuples in R is n, and the number of tuples in S is m. And what is the time complexity running this algorithm? It should be like a no-brainer to you guys. N times -. So that's very slow. So you're visiting every combination of the tuples, and then you're checking whether these joining conditions are met, and then you're checking whether the where condition is met, and then only then you add the tuple to the result. And in practice, it's very rare that we're using a nested for loop to implement that, but you can imagine this is the most naive implementation. So okay, enough with theory. Let's look at a real database called beers. So in this beer database, we have the brewers, we have beers, and we have a bunch of bars, and these bars are in Sydney, and we have a bunch of drinkers. So drinkers can visit bars. This is a many-to-many relationship, and drinkers can like beers, and bars can sell beers as well. And beers need to be made by certain brewers. And one thing you notice about this schema is that every entity, we're only dealing with strong entities here, so that's better, that's easier. And every strong entity has the primary key called ID. So in this case, it's very important for us to use that object-oriented syntax to specify which ID you're talking about. So if everybody is using ID, then when we're joining them, it will be very confused. What ID are you talking about? So for every entity, we have a table, and for the relationships, for likes, for frequency, and sales, we have 3 tables because they're all many-to-many relationships. So basically cross-reference, just like the enrollment table. And then for the makes relationship, this is a one-to-many relationship. And just by looking at the semantics, you can kind of understand how this works. Like a brewer can make a bunch of beers, and it may not make any beer, but a beer needs to be made by exactly one brewer. So, and the way we handle this in the database is that we ask each beer to store the brewer of the beer instead of the other way around. So that explains why we have these tables. And then we're going to demonstrate how we can answer these questions. So we have prepared like about 15 questions. We'll probably get to like 10 or 11 of them today, and we'll start from easy ones. So we'll start from the single table queries. So how many? So a lot of times this could be among the first queries that we run on the database. How many beers? How many different beers are there? So this is a single table query because we can basically look at beers and then we can count the number of beers in there. So count star is basically counting. So if you're not specifying what rows, what columns you're counting, you can use count star to basically count the length of the database. And because in beers table, beer's ID is the unique identifier of the beer. So every beer should have one beer's ID. So probably a more robust way of counting this is we're counting the beer's ID so that we don't really get any duplicates. So we'll probably demonstrate some of these after we go over them. And the second question is also kind of easy. How many brewers are there? So the first thing we look at questions like this is that we first look at the schema and we identify what part of the schema is relevant to this question, because we're only asking question about brewer itself. So basically we're going to use the brewers table, and brewer has name and country, but and also ID is the unique identifier of brewers. So if you want to know how many brewers are there, we basically select the whole table and then put count star after select. So here we're basically renaming them. So these are some. So basically here we're renaming it to the number of beers. If you don't do that, it will give you a different name. So if you want to really control the name of the column in your result, you can always use as to rename the columns. And so this is slightly more complex query. So we want to answer, so by looking at a question, we want to answer what beers are made by TUIs. And TUI is I'm not much of a drinker, but obviously TUI is a brewer. So let's go back and look at the schema and decide what information we need, what tables we need from our schema. So the good thing so I remember a student asked us, why do we bother with the ER diagram when it is the exact matching from the tables? Well, in real life, we could end up with like 10 tables or hundreds of tables. And if we have that big schema file, sometimes it's very hard to identify which tables are relevant to a question. Well, with tools today, it can be faster, but still we need to go through like a giant file. And the good thing about ER diagram is that it gives us the exact structure of that database. And just by looking at it, we know that we need information about beers and who made beers. So it has nothing to do with who likes the beers. It got nothing to do with who sells those beers. So we're only interested in the beer part and the making part as well as the brewer part. So that that leaves us with these two tables, the brewer table as well as the beer table. And the reason we should map the one-to-many relationship is, as you can imagine, we are creating a brewer's table, and in the beer table, you can imagine there is a column called maker or brewer of the beer that references the brewer's primary key, brewer's ID. So what we should do here is that we should join these two tables. So basically we should select from these tables, and after from we should put brewer and beer, and in the where clause we should specify that we need to match beer's maker to brewer's ID. So I'm asking you to, basically at this point I'm asking you to imagine that, but this is the real code. So notice that it has a slight, it is different from the approach that, it is slightly different from the approach that I've described. So this is an explicit join where you're explicitly saying that I want to join the brewer's table and the beer's table. And here it creates another name for a short name for beers. So we call it B. And for brewers, we call it BR. And we're explicitly saying that we want to join these tables on this condition. We want to match the brewer of the beer. Yeah, it's your phone. Yeah, it's your phone. That's right. So we want to specifically match that. We want to say that we want to match the beer's brewer to brewer's ID. So and after that, we want to throw in the brewer's name is Tuis. And the reason why I say this is an explicit way of joining is that there is actually an implicit way of writing a join. So we can write a join without specifying it is a join. So we can basically throw this information, we can throw that part of information into the where clause, and the database engine will understand that this is a join. So what we could do is that we could still select these, we can still select these columns, and we'll need to specify that we're selecting from beers and we're selecting from brewers, and we can also give them short names like B and BR. And then instead of specifying a join, an explicit join, we can put that information on the where, and we can say where brewer name is Tuis, and also we need to specify that b.brewer equals brewer ID. So we can put that on the where as well. So that's a way of writing, that's an implicit way of writing a join. So I personally prefer the implicit way, but you can do either one. So let's look at another one, and maybe we can do some demonstrations of these and have a better idea of how this works. And this question asks, we want to show the beers with headings beers and brewer. So basically, we want to show the beers and their names. We want to show the beers as well as who made the beers. And we want to control the column name in the end result. So we don't have to worry about that in the beginning stage of problem solving. So first of all, we look at what tables we will be using. So we already talked about, we have the beers table, we have the brewers table, and we're asking the beers to store the brewer as a foreign key. So we'll be joining those tables again in the same way. We're saying that beers, give it a short name B, brewers, give it a short name BR, and then this is a joining condition, beers brewer equals brewer's ID. And only in the end, we care about the names of the attributes. So if you really care about names of the attributes, you put beer's name, b.name. So basically, beer, it will extract the name attribute from beers and rename it as beer. and it will extract the name attribute from brewers and rename it to brewer. So this is why we use entity.attribute convention here, because if you look at the tables, both of these, if you look at beers and brewers, they have the same, they both have an attribute called name. And if you don't specify where is that name coming from, then it will be then database system will be very confused, and it will not know which attribute to rename. So basically, we need to specify that, okay, for beer's name, we name it to beer, and then for brewer's name, we name it to brewer. So that's easy. And for question 5, we want to find the beers that John likes. So first of all, we still need to identify the tables. So we want to find out which beers does John like. So this kind of involves 2 entities and a relationship. It involves the drinker's entity. So John should probably match the drinker's name, and it involves the likes relationship, the likes table, and it also involves the beers table, because in the likes table we don't really store the beer's name. So it involves drinker, likes, and beer. It involves these 3 tables. So we need to join these 3 tables together, and then we need to match that the drinker's name is John, and we need to match that. We need to match 2 foreign key constraints. So basically, we need to match that drinker's ID is equal to likes drinker, likes.drinker. We need to match that beer's ID is matching likes.beer, 2 conditions. And then we need to match that drinker's name is John. So that's the only 3 conditions we need to consider in this question. So basically, we need to join 3 tables, and we need to write 2 join conditions, and in the end, we need to say that the drinker's name is John. And so this is a step-by-step way of looking at this question. So and in the end, this will give you. I always like to start selecting every column, all of the columns from the join tables, and in the end, depending on what the question is asking, we actually retrieve that required column. Okay, I feel like we can just do some demonstration in VLab here. CSE gateway. Oh my God. Okay, denominator, HDB02, great. Okay, let me just check how many people have. Okay, 410. Still need like a couple of hundred people to set up the PostgreSQL server. So if they don't, I will find out who didn't do that and send them send them an email reminder to do that. Because if they don't do that, it will be a big problem. Let me go to. Okay, this is my code 3. Okay, I think we start. I've already started the. I've already made a database, so let's just. Okay. Okay. So this is the database we've been talking about. So I think it is better if we examine the tables that we have just talked about. So for beers, beer's ID, brewer. So basically, remember we had let me go back to the schema. Okay, not this schema, the beer schema. Okay, remember that we talked about beers and brewers. So here we can see that in beers, we're storing the brewer of the beer, and this will be a foreign key referencing brewer's ID. And how do we, so the first problem was how do we find the number of beers? So first we look at all beers. And one tip is that if you don't want to look at the whole table, you can use limit to limit the number of rows you look at. So I like to limit it to 5 rows. Okay, so if you look at, so that will be easier for you to look at, and to get the number of beers, you can just put count star. Now the column name is automatically to count. So it is automatically given count as the column name, and if you want to make this column name more informative, you can just say that you can rename it as that's the number of beers. Okay. So if you do that, it will rename the column. And let's just say that, let's just show you the two ways of, let me show you the two ways of joining the tables, and then we'll take a break. So I'll show you the implicit way first. So let's select from beers. Let's call it B, and we need to select from another table, which is brewer. Call it BR, and we need to say that beers dot brewer is brewer ID. I think that's the one. If you do that, brewer does not exist. I think it's brewers or something. I think I missed brewers. Okay, brewers. Okay. Here I don't have to write the whole thing. I just say that. And this is a giant table, as you can see, because we didn't really specify which columns that we want. And let me give some filtering conditions, maybe based on the brewers. So maybe we need the brewer from Australia. Okay, so we can basically. So here I'm writing it in an implicit way that we don't really specify the join, but we put that as part of the where clause, and we can pad on another condition. So if we have two conditionals, we need to pad them with and. So what else do we want? We want the brewer's country to be Australia. We want br.country needs to be Australia. Let me look at what beers are in Australia. And if I don't do that, it will wait for me to enter semicolon. And we still got too many of them. Let's just limit to like 10 of them. And this will be 10 of the, so this will be the joining result between beers and brewers. And if you want to get, and this is the end result because we have selected everything from the joining. What if we just want to find the beer's name that are brewed in Australia? And as you can see that if we don't specify, if we don't actively rename them, they will just get their original name from the tables. So this ID is from the beers table, name from the beers table, and this ID is from the brewers table, and this is the brewer name. So it gets super confusing. So what we want to do is that we want to grab the correct column and name it in the informative way. So probably what we want is that, this time we'll not limit to 10. What we probably want is that we want to select the B's name, B.name. I cannot type here. And this will give us a list of 21 beers made in Australia. and maybe just give me 5 of them so that I can see them more clearly. So now I'm getting the beer's name, but this is not very informative, so I can name it into like Aussie beers. I can name it Aussie beers. Aussie beers. And then, okay, I typed, I got a syntax error in here. So it should be beer's name renamed to Aussie beers. So now we got like 5 Aussie beers here. And another way of writing this is that we can really specify, so we don't have this part. We move this joining condition into an explicit join. So we delete that part. And in here, we're saying that beers B join from table beers B join brewers BR, and then we need to specify that B.brewer is matching brewer's ID and up. So basically, we are putting the joining condition in an explicit join. So this is not my favorite way of doing it, but you can do that as well, because you have to write additional syntax. You have to write A join B and then put on certain columns. So my preferred way is actually just write it like this, because this is a good old select from where block. Select from where block. After from where we list the tables. After from we list the tables, and in where we put the joining condition in there. Okay, that's a good place to take a break for 10 minutes, and then we'll come back with more demonstration. All right. That's me. Great. So let's get back to solving those questions. So we got a question from the online string. So I think it would be better if we work through each question one by one instead of like demonstrating in the end. So I think we have, let's see. Let's connect back to the database. And so we have just demonstrated how to do implicit joins as well as explicit joins. And let's look at the next question. I think we're at, okay. Which beers does John like? Okay. So this is another similar question. So find the brewers whose beers John likes. So basically we need to look at the drinkers because we can only get information from drinkers named John. And we need to find the brewers table and we need to look at the likes table. So let's go back to the schema and think about what tables we need. So we need drinkers table, we need likes table because we need beers table and we need brewers table. So we need all these tables. We need drinkers table, likes, beer, and makes, and brewer. So so basically we need to join probably 3 tables and we need to have an additional. We'll probably need to join 5 tables, and we need to have an additional constraint drinker is John. So in the explicit way, we can write, we can match the, we can first match beers and drinker with likes. So on likes, we need to match that the likes drinker is actually drinker's ID. We need to match that beer's ID is matching likes table's beer, and we also need to connect the last table from beers and brewer, which is what we have already done in the first few questions. We need to map beer's brewer to brewer's ID. So these are the joining conditions we need to join those tables, to join drinkers table with likes, with brewers, and with beers. And in the end, we need to put we need to specify that drinker's name is John. So we can do that step by step, and in the end, if the brewer's name have duplicates, we need to remove that. So let's do this question, and let's just memorize what tables we need to join. We need to join beers and likes and drinkers and brewers. So we'll do it in the implicit way. So let me investigate the table structure again. So this is what I meant by working this problem step by step. So we can join beers. We need to join brewers, call it BR, and we can join drinkers. Let me just start from the last query, which will be easier. So we need to join beers and brewers, and we will need to join drinkers, call it drink, and we need to join likes, which is L, and we need to specify beers brewer equals brewer's ID. We need to specify that drinkers. Let me go back to the schema. We need to specify that drinker's ID is matching likes drinker, and beer's ID is matching likes beer. Okay. So basically, we need to match those two entities with the likes table. So we need to match drinker's ID to likes drinker, and we need to match beer's ID to likes beer. And what else do we need to match? So we have already matched drinkers and beer, and we have matched beers and brewers. So that should be enough. That should be end of the join. So let's just get rid of, let's look at that. Let me get rid of the select. Let me get rid of the column after select and just return every column from the join. So here, basically, we're specifying every tables we need to join. So beers, brewers, drinkers, and likes. So basically, we're joining from here all the way up to here. And we're joining likes drinker to drinker's ID. We're joining likes beer to beer's ID. And then we're joining beers brewer to brewer's ID. So we're joining those conditions. After joining all those conditions, it should give us a giant table. This is a giant table, and it's very hard to work with. So what I like to do is I like to limit the result and actually see the structure. Okay, it turns out that there are too many columns over there. So let's look at, so this is the correct join, but now we need to look at what columns that we need. We need the brewer's name. So basically, after all these joins, what we need is actually the brewer's name. So we need to select the B name, and then B brewer's name, and see how many are there. So all the way up here, we need to specify, what do we need? We don't need the beer's name, but we need brewer's name. So brewer is abbreviated as BR, and we can say brewer's name. So we got these brewer's name, and as you can see that, why do we have like duplicates in here? So it is very important for you to understand why your result has duplicates. So let's look at the brewer's table. The brewer's table, the primary key of the brewer's table is brewer's ID. So brewer's ID is the only unique identifier of brewers, which means that you could have one brewer with ID 1, you could have another brewer ID 2, they could have the same name. So we allow them to have the same names, but in the database, we still treat them as different brewers. But in here, because you only want to get the names, so we want to remove the duplicates. The way we remove duplicates is by adding distinct to it. So as you can see, that brewer's name has duplicates. There are 2 carton brewers and there are 2 TUIs. So we add distinct to it, and it will give us the distinct brewers that are the distinct brewers. And I think we're missing one piece of information is that we need to specify that these are the brewers liked by John. So let's just pad that in the end. So the good thing about the implicit way of writing join is that you can always pad another condition. So we want to make sure, we want to specify that the drinker is John. So where's drinker? Drinker is D. So we want to make sure that the drinker's name is matching John. So if I use lowercase John, this won't work because although SQL is case insensitive, the string literal should be exactly that. If you put John, it will say cannot find any brewers liked by John. So you need to use the string literal, and it will give you 5 brewers. So this is how you can solve complex queries step by step. So first you identify what tables are needed, and you need to look at the original schema and find out what are the joining conditions of these tables, and in the end you specify additional constraints as well as the columns that you will need. And one thing that you might feel not very happy about is that you ended up with this very long SQL statement. So it can get very weird and long, and in the end, we still need to write one giant SQL statement. So I'll show you how to avoid this by using views. So in the next few questions, I'll probably show you how to use views. So let's just look at this. So how many beers does each brewer make? So how many beers does each brewer make? So this is another problem that involves how many tables? It involves 2 tables because we're only talking about beers as well as the one-to-many relationship with brewer, and we're storing brewer of the beer in the beers table. So it only involves 2 tables, beers and brewers. And note that here it says that we need to find out how many beers does each brewer make. So this is not a global query anymore. This is specific to each brewer. So in this case, we need to group the data by brewer. And one thing you need to understand whenever you're grouping, so whenever you're counting, you want to use the primary key of the grouping of the table that you want to group by, of the table. So let's say that you want to group by brewers. You don't want to group by brewers' names. You want to group by brewers' ID because brewers' ID is the unique identifier of brewers. And in the database, we treat 2 different brewers with the same name as different brewers. So and also when you're counting, you want to count the primary keys because they're the unique identifiers. So let's just start with a very simple join. So if we just select from, okay, I'm typing this over and over again, brewer, and what else? I'm joining from beers, and I'm specifying that brewers.id is beer.brewer. So this will give us, I think it should be beers. This will give me the join. So now I want to group by the brewers. So what I want to do is that I want to tap pad group by here. And after that, I should specify the column or columns that I want to group by. So I want to group by brewer's ID. So I want to group by brewer's ID here. Let's group by brewer's ID. Or you can get away with grouping by name if you want to, if you don't care about different brewers having the same name. So and then you see that once you group by them, you need to once you group by something, then you cannot just select everything. Once you group by a column, the column by which you group by must occur after select. So you need to put that there, because now we're looking at the data for each group. So for each group, we need to select the brewer's ID, as well as, let's just throw in a number of the number here. So basically for each group, basically it will present the result in different groups, and it will give you the brewer's name or ID, and then after that it will give you an aggregate. So basically here you need to apply some type of aggregate function for each group. Here we're just going to put the number. So maybe it will be more informative if we use name rather than ID. So if you put the number, if you put name here, if we group by name, you see that we can get the number. We can get the number of rows corresponding to each brewer. So basically, we're getting the number of beers made by different brewers. So here, counting is only the easiest kind of aggregation you can apply to each group. And you can also apply other aggregation here. So let's see what other aggregation can you do that you can apply to it. So what if for each brewer you want to get the maximum price or something, but that would involve more than one table. Let's just see what else you can apply to it. So between brewer and beer, well, I think it makes more sense if we're actually talking about price here, where we can get the maximum price sold by different brewer. At this stage, the best you can do with aggregation function is counting the number of beers made by each brewer, or getting the aggregation of the beer's name. So that's not very interesting. So we're just gonna stop here and be happy with number of beers for each brewer. And here, because we want the names to be more informative, we can just say that number of beers per maker, and then it will give us a good column name right here. So that's how you can do group by. And remember when we talked about the having clause? The having clause is adding additional constraint when you're grouping. So I think this is a good place where we talk about where we use the having clause. So here we can add another constraint, having. Let's just say we only look at the brewers as well as the number of beers they make if the number of beers is larger than maybe 3. So this piece of information, having count larger than 3, is applied to this aggregation row, and it is applying post-processing to the table that we have seen here. So basically, if we don't do that, it gives us this table with all of the brewers and even the brewers who have only made 1 beer. And if you want to make sure that we're getting high quality brewers that has at least made 3 beers, so I'm just going to put greater than or equal to 3, then it will apply post-processing to the table that we have seen here, and it will only keep the ones with number of beers per maker larger than or equal to 3. So having the having clause only applies when after group by. So if you want to throw in additional filtering conditions that is relevant to the whole table, you want to throw them in where clause. So the having clause only applies when you want to further apply further filtering after grouping by certain columns. Okay, now that we got group by and aggregation out of the way, let's look at what other queries we can do. So this is basically we can group by different brewer and get a number of beers. And another query that we could run is we want to find out which brewer makes the most beer. So this becomes a slightly more difficult problem where there are actually two ways of doing this. So if you don't have join, how do you propose you do it? If you don't know how to use SQL, how do you propose you want to do it? Well, you could run the same query, grouping by, let's just say the same query here, grouping by the brewer's name, and then here we got all of the number of beers per maker. But now we want to get the brewer who made the most number of beers. How do you do that? Here you can either first compute the maximum number of beers made by a brewer, so basically 5, and then you can map that value back into this table to recover the brewers. Or what you can do is that you could basically sort this table by the second column and then only grab the top part of this table. So think about these two approaches. So let's just apply that one. So let's just order by the number of beers here. And we want to make sure that it's ordered in a descending order. So now it's from highest to lowest. So this will give us highest to lowest. So if we do that, if we add on an additional order by clause, it will order the original table that we have seen by the second column in a descending order. So on the top of it is the brewer that has made the most beers. And after that, followed by Tuis and James, I don't know how to pronounce that, James Square, I'm gonna butcher it. They made 4 beers and they're at the second. And if we want to get the brewer who made the most beer, what should we do? We can just limit to 1. Well, that's one approach. We can just, limit 1. That looks pretty good on paper, right? Let's just investigate that table again. So right now, we only have one brewer who is at the top. What if we have 2 brewers and both of them made 5 beers? And how do you know if you want to limit 1 or limit 2 in that case? So that becomes a harder problem, right? So in theory, this could work. So if you just limit 1, you're just getting 1 brewer who made the most beers. But what if there are multiple brewers who are making 5 beers? Then then this shouldn't work, right? Because we're only getting 1 of them. What if I want all of them? Yeah. That's exactly what I'm thinking. So she's suggesting that what if to handle the case where we have multiple brewers corresponding to the same maximum value, what we could do is that we can first compute the maximum number of beers made by a brewer, and then we can map that back to the table. So let's do that real quick and see how we can make this work. But that is an additional steps. So I think this is a good place to introduce views. So a view is basically kind of like a virtual table. The syntax is you can create a view as something, and then followed by a SQL query, and it will store that SQL query in the database. And when, let's just create a view with exactly this, okay? In the very beginning, I'm just gonna say that I'm going to wrap all of this into a view. I'm going to create view sum table, summary table, as the following SQL statement. So what I've done is that I've created a view called, sum table is a terrible name, summary. I'm creating a view called summary. And how we create it is that we are defining this view as the query followed by that. So this should create a view for us. And the way we use view, this is the beauty of view. The way we use view is that we can treat it as if it's a table, but it's not really a table. Because within the database, it does not create an additional result table, and it does not take up additional space. But when we want to use the view, we can treat it as if a table. So let's just say that I want to see what is in the view. Then the query in the view is only executed when I'm using it. So let's say that I want to use this view summary, and then I can just select from summary, and then it will give me exactly that. This is very nice. So, so view allows us to tackle a problem into smaller steps. So let's get back to your idea. What did you want to do? You want to find the maximum number of beers made per maker, right? So I just create another view called create view called a max beer adds. The beauty of view is that we can create view based on another view. So basically, we're creating another view called max beer. And how do we get max beer from here? We just select from this view and then apply maximum to the second column. So we can just do select maximum to the, so I'm going to type this all out. I made this number of beers per maker. Select this from our previous view. Our previous view is called summary. So basically, we can treat it as if it's a table. We can, from summary, and now we have a new table. And now we have a new view called maximum beer. So let's look at here. Now you can see that we have created not only tables, but also views. And we can look at the second view that we have created, which is max beer. Then it's just 5. This 5 is exactly what we want to get our final view. So what if I want to get the brewer or brewers corresponding to the maximum beer? Well, I can do an additional join with summary and the max beer and mapping those conditions, and then in the end, I should get the list of brewer or brewers with the most beers. So what I can do is that now this is the final view, so maybe I don't bother with the view. So I'm just going to try things. So I'm just going to select everything from the summary table and the maximum beers table, where the summary table number of beers per maker. My God, I think that's a terrible name. Equals max beer dot number. Let me see. I think it has all kinds of syntax error here. Let me just investigate the column names to get them right. Select from here. Limit to. Okay, it's called number beers per maker again, and then let me look at the max beer. Max. Okay. So basically, our previous query should be summary number of beers per maker equals max beer max. Okay. This is called max. Okay, so now what we did is that we're joining the summary table with the max beer table, and then we match the number of beers per maker to the maximum value, so just like you did. So here is giving us the same result. We're getting the same brewer again, but this approach is much more robust, especially if we have more than one brewer corresponding to the same maximum value. So this is an example of writing more robust queries using views in a step-by-step manner, and that should handle more complex situations. And if I want to, like this is probably what you should do in the assignment. What if I want to, now this is the final result, and it works on different scenarios, so I want to store this query. I don't want to just use it one time, so I want to do create view called, maybe this is Q6, so I'm just going to create Q6 as this. So I'm going to define this nicely written view that are dependent on other views as question 6. And if you do that, then every time you select from Q6, you will see what we want. And the beauty of this is that you can create views based on existing tables, and then you can create views based on the views you've created and the existing tables. And the query that you're storing in these views don't get executed unless you are querying it. So it doesn't really create additional tables within the database. It only stores what the query is. And under the hood, when you're selecting from Q6, it will look at the definition of Q6 and see that, okay, Q6 depends on two other view definitions that are summary and maximum beer. And then it will look at the definition of summary and maximum beer, and those are based on beers and brewers. And they'll grab all of these views together, and then they will optimize and then find out how to join those tables to get this final result for you. And another thing that you should understand is that we have only defined a view. Basically, this is one way of looking. A view is one way of looking at the database. So what if the database changes? This will change as well. So basically, this defines a kind of like a function or a query on the database, and it does not just store this result. It never stores this result. When we make when we change the database, the result of this query will change accordingly. Okay, think that's a good example of how to use views to do things step by step. Well, this is the original approach where you're assuming that is only one maximum entity, but if we have more than one, then we should do the mapping and make it more robust. Let me see what other questions that I want to go through. I think one thing so we have gone through what is a view is, and so creating view will be you'll create many views in your assignment, so creating view is super important. So a couple of things you want to remember about views is that you can use views as if they are tables, but they're not actually tables, and the view is not executed until you do select from view, upon execution time. So the view is not executed until you select from it. And also, views can be built on other views as well as other tables. So basically, you can treat them as you can treat them as intermediate results, and then you can build on that intermediate result to get a more complex views. So in the assignment, you probably want to use create or replace view. The reason why you want to use create or replace is because you're going to write all that into the SQL file, and you're going to reload that SQL file over and over again. And if you always recreate the view with the same name, what ended up happening is that the SQL will complain, hey, we created this. Don't do that anymore. So basically, in the SQL file, you want to say create or replace. Otherwise, in the second or the third term, in the second or third run, it will not update your view. And if you don't like your view anymore, you can always drop view, and then you create your view again. So before we go, I think there's something that I like to talk about, which is set operations. Set operations are very useful. So I want to talk about union, intersection, probably intersection. So where's intersection one? Okay, let's find out how do we find the bars where both two drinkers drink. Well, so here, now that we know how to create views, we can break this down into different steps, and each step will be a view. And in the end, we'll combine this view to make our final query. So first of all, we can create a view for the bars where John frequents. And then we can create a view for the bars where, I don't know how to pronounce his name, Gernot. Is that the correct way pronounced? Gernot? Gernot. I'm going to go with Gernot. So how the bars where Gernot frequents, goes to. And in the end, we're going to do the intersection of those two views. So basically, we're going to select bars from John's bar, and then we're going to select the other bars, and then we're going to do an intersection. And the important thing about set operations is that you need to make sure that the participating tables have exactly the same shape. So let's just say that the first table has A, B, C columns, and the second table has A, B column. And if you ask SQL to do an intersection of those two tables, SQL does not know what you're talking about because they are inherently different entities. So whenever you do intersection, whenever you do union, and whenever you do set difference, you need to make sure that those participating tables have the same shape, meaning that they have exactly the same type of columns. Okay, that's demonstrate how to get demonstrate how to get the intersection of those bars and see what happens. So how do we get the bars where one person frequents? Let's look at the schema again. So you need to identify the tables first. Okay, here it is. So basically here we need to look at drinkers table and the frequency table as well as bars table. And in the end, we need to find out the bar names that are frequented by both people. So that first, we need to join drinker and frequency, and then we need to join frequency and bar, and then we need to add those two additional constraints on the drinker side, which is whether it's John or Gernot, and create two different views. In the end, we need to do an intersection. So I think it makes sense for us to first join these tables, and we can define a view like that to make things easier. So let's just create a view called O. You should come up with better names than this. So I'm just going to select everything from where? From drinkers, frequency, and bars. Drinkers, frequency, and bars. So drinkers D, frequency F, and bars B. We can call it BA because we might need to work with beers later, and we need to specify the joining conditions. So how do we join drinkers and frequency? Well, we need to specify that drinker ID, which is the ID, drinker's ID, is matching with frequency drinker. Okay, so drinker's ID is matching frequency drinker. What else do we need to match? We need to match that the bar here, this should be a foreign key pointing towards bar's ID. Okay, so we also need bar's ID to be frequency bar. Is it bar or bars? Bar. Okay, that should be create view. I think all is a very bad name because I think I'm just going to call it helper. Create view helper. Okay, it's saying that the column ID specified more than once, so we cannot get. So here it's saying that the column ID specified more than once. So basically, when you're joining them, the IDs get specified more than once, and when you're selecting all of the columns, it got confused. So what we really want is, we want to get the drinker's name and drinker's ID, and then for bar's ID, we need to rename them to bar's ID. So basically, for drinker's ID, we need to name it, for drinker's name, we can name it as drinker, and we need to mapping from drinker and bar. So we need drinker's ID, drinker's name, bar ID, and bar name. That's all we need. So drinkers, and also we need bar name as bar. Okay. Table bar. I think should be. Oh, bars. Okay, my bad. Okay, it should be a renaming. Okay, that's good. So now we have found the correspondence between names and drinker names and bar names. Let's look at the helper view that we've created. So now we got all of the drinkers and all of the bars. Now let's map the bars where John goes to. So let's just create another view called John bars. John bars. As what do? We need to use the view that we just created called helper, and then we need to map drinker to John. So we need to select the bar names from helper, and we need to specify that drinker is John. Drinker is John. And then we can do the same thing with the other drinker. So if we look at this, if we investigate this, this will give us 4 nice bars. And let's create another one for the other drinker. And then we're going to create another view called Gernot bars. Okay. And if we select from the second view, you see a list of bars as well. And now we need to create the final view. We need to select from John's bars, and we need to intersect with another table, which is another person's favorite bars, and then we'll get the bars liked by both of them. And the reason why intersect works here is because both these tables that are participating in the intersection, they have exactly the same shape. So if you look at John's bars, it has only one column called bar, and if you look at Gernot bars, it also have exactly one column. And this is getting the bars where both people like. So what if I want to get bars where either people like? Well, that will be a union. Let's change to union. It will give us 5 bars. So basically, all of the bars liked by John, and the union, all of the bars liked by Gernot. And if I use except, it will perform a set difference. Except. So basically, it will take set 1, and then it will remove everything from set 2. So basically, S1 minus S2. So it will give me the bars liked by John, but disliked by Gernot. And if we do this other way around, you will get the bars liked by Gernot and not liked by John. So, and if you union these together, that will be a symmetric difference. So that's something else. So hopefully you understand how union works, how intersection works, as well as how except works. Okay, that's probably the most important part in today's lecture. So, so basically the takeaway is you need to practice a lot to, when you go home, my suggestion is that practice those single table queries first, and practice writing the join conditions in both implicit and explicit ways, and then practice grouping by as well as having afterwards, and then in the end practice how to create views to tackle these problems in a step-by-step manner, because that will be a very important skill that will be beneficial to you in the assignment. And we'll talk more about how to write simple queries in next class, and thank you very much. Yeah, hello.
So when we're editing the .SQL file, are we doing it in Vim or is it more?
I did it in Vim because demonstration purpose. Obviously you don't want to use